The next topic of today's lecture is about the operating system's boot sequence and its general operation. So what happens at the boot of your computer? So when a computer switches on, it does the same exact thing that Venus does. The CPU executes instructions from some start address, and this start address is normally stored in flash ROM. This will start loading in the BIOS, which is the first step of our computer boot sequence. So this will basically find a device and load in the first sector, which is the first block of data. Next, we have our bootloader, which is stored on disk, and it will actually load the operating system kernel from disk into memory, and then it will actually jump to it once it's finished loading all that stuff in. Next, we have the operating system boot sequence, which will basically just initialize itself and services and drivers that it needs to be able to interface with your computer and just run in general. And finally, once that is done, it will launch the init, which essentially will allow us to launch applications and that wait for input in loop. So this will basically be running until your computer shuts off, and this will allow us to run terminal, desktop, those types of things. So this is the general sequence of how we actually start up a machine. Applications are normally called processes in most operating systems. They are created by another process calling into the operating system routine, usually using a syscall. We'll talk a little bit more about those later. The method to actually launch a new process is actually system dependent, and it really depends on the operating system. For example, Linux uses fork to create a new process, and execve to load applications. So when you're loading applications, we really load the executable from a file on disk using some system service, and it will put the instructions and data into memory. For example, you remember those .text and .data sections. It will actually load those into the correct locations of our memory. It will then prepare our stack and heap, and finally it will jump to argc and argv, and then jump to the main function, so then the program can start executing. But what if something goes wrong in an application? It can crash the entire machine. That would be horrible. What about if I had a malicious application? Couldn't that steal data? That would be horrible. So the operating system needs to be able to enforce resource constraints to applications. For example, we need to limit who can access certain devices. We also need to protect the operating system from applications. And CPUs normally actually have some supervisor mode bit in there, which allows operating systems to be able to access certain instructions which a user might not be able to access. So this is actually very useful. One thing that we'll have to talk about in a little bit is isolation, because isolation is also very important. For example, I wouldn't want my malicious program to be able to access my password manager. That would be horrible. You can also change out a supervisor mode using a special instruction, but you cannot jump into it unless there is some interrupt or trap of some sort. And here is the image again of a general breakdown of how a user level versus kernel level versus hardware level interface works. What I was just discussing is there's normally a supervisor bit, which means whenever I'm executing stuff in here, that supervisor mode bit is set, which means I should have access to more instructions so I can do some of the systems level stuff. For example, say I needed to keep track of which process I was running or that kind of stuff, I should only be able to access it in the kernel. The user should not be able to access that kind of stuff. This also allows an application to crash, but not kill the entire operating system, because the operating system is in a separate level, which essentially will allow it to take care of whatever the failure was of the application and allow it to continue to run. So how does the operating system switch back to the OS? Well, the OS can set a timer interrupt, which basically after some set amount of time, this timer, it will trigger an interrupt, which will allow us to drop back into supervisor mode. And so it will allow the operating system to execute some more code. So what if we want to call into an operating system routine? For example, say we need to load a file or read to it, maybe write to it, maybe we want to launch a new process, maybe we want to send data, who knows? Well, in that case, the application would have to perform a syscall, which basically will set up function arguments into registers, and then it will raise a software level interrupt, so then it can communicate some data into the operating system. We do not want an application to be able to jump directly to an operating system location, or a part of the operating system, because that could lead to security vulnerabilities. For example, say I have a verification that a user has access to it. If the user is able to directly jump, they can jump past my verification check and jump straight into the meat of the code. So the operating system will perform the operation that the syscall requested and return back to user mode. This is the way the operating system can actually mediate access to all resources, including devices like the CPU itself, and other devices like hard drives and those types of things. Venus actually provides many simple syscalls using the ecall RISC-V instruction. So ecall is really the syscall in RISC-V. So how do we issue a syscall? Well, in Venus, we would place the syscall number in A0, and then we'd place the arguments for that syscall in A1 through A7, and then we'd issue an ecall. Venus understands what each of these sys numbers is, and it will do whatever it needs to do based off of what the operation told it. So this is how your RISC-V has been able to produce output all along. So the eCall details are also dependent on the application binary interface, or ABI. So that's why you might have an application that was written for Venus not work with an application that is written for Linux, RISC-V Linux to be specific. So here's a quick example of an eCall or a syscall in Venus. We want to print the integer in S3. So what we're going to do is we're going to load in syscall number 1, which tells us that I want to print whatever's in A1 and it is an integer. Next, I'm going to load S3 to A1. That's why I'm doing this add operation. So now I have A1 is 1, or A0 is 1, and A1 is whatever S3's value is. Finally, I'm going to call eCall, which is basically going to interrupt the user process, go into the operating system, then the operating system is going to read whatever A0 is, figure out that we want to print the integer, and finally print A1 to the screen. So Venus has a whole bunch of different environmental calls. Here's just a quick example of a few of them. I recommend you go to this link to see all the different cool operations that Venus can do, and you should have had some experience with actually using these with Project 2.